All right, so my name is Kat. I'm here with some of my lovely coworkers and the amazing Professor Paul Delaney. He is a professor at York University and Department of Physics and Astronomy, and the inaugural Carswell Chair for the Public Understanding of Astronomy. He is the coordinator of the very own Alan I. Carswell Observatory, and he promotes the use of the telescopes for education, research, and public outreach. So today he's going to give a really cool talk on water in the universe. So I'm going to hand it over to him right now.
Thank you very much indeed, Kat, and to all of the folks at ASX for inviting me. It doesn't take anything for me to pop along and talk about astronomy. Let me first off, though, bring up the slide share, make sure that's all working. Okay, somebody should yell loudly if it looks as if you can't see the screen. In the absence of yelling and screaming, I'm going to assume that we are in fact live. Okay, so as Kat indicated, I am from York University, and before we sort of plunge in, pardon the pun, to this topic, which I think is really a surprising topic. If you look back over the last 40 or 50 years of our understanding of the solar system, water was thought to be really, really scarce. That the only place that you would find water in any significant way was literally right here on Earth. That whole notion, however, has changed very dramatically to the point now where we fully expect to find water almost everywhere we go. And not necessarily, of course, in a liquid form, but of course, ice, frozen water, is still water. Anyway, we'll talk more about that as we have an exploration of the solar system. First off, I do want to put in the plug. My dean really likes it when I plug things like this. If you have the opportunity to, well, normally I'd say, walk up the road, but of course you don't have to do that these days. You can just turn it on Zoom. There are opportunities for you to participate in some of the activities of the Alan I. Carswell Observatory on Monday nights with our online public viewing program from 9 till 10, which runs coincidentally with our York University radio show, which is on astronomy.fm, or on Wednesday. In fact, after you finish with this presentation, you could pop across to YouTube, to our YouTube channel, and have a listen to the observatory team as they regale you with one thing or another. It's a different topic each Wednesday evening. If it's clear on either of these nights, Mondays or Wednesdays, you have the opportunity to virtually look through our 1 meter class telescope. So there are many, many ways that you can continue your love of astronomy despite the pandemic. As I said, we do have a 1 meter class telescope. That was the gift from Alan Carswell about 2 years or so ago now. And here it is in the top left-hand corner. It truly is a beautiful 21st century telescope, spins on a dime, wonderful precision pointing, and it really is just a wonderful piece of equipment to use. And we use it for our first, second, third, and fourth year undergraduate astronomy classes. And the observatory team is happy to show it off on Monday and Wednesday nights as well. Okay, end of ad. Why is water, such an intriguing topic? Well, the very short answer is it's associated with life. Life on this planet simply could not exist in the absence of water. And it doesn't matter whether we're talking about humans, animals, birds, fish, bacteria. Water is the driving molecule that allows the proliferation of life that we have on this planet to actually exist. And so for the last 20, 25 years, most of the space programs, particularly the Russian and the American space programs, have been heading out into the solar system with the mantra, follow the water. And the reason that that mantra is there, because if we are following water, the signs of water, the presence of water, the existence of water, it maximizes our possibility to find life. Now, that's not to say that life could not necessarily exist in the absence of water, but at this point in time, all of our biology suggests that water is an absolutely key ingredient. And so instead of trying to think outside the box at this moment in time, searching for life in our solar system is equated to the search for water. Certainly life in other formats may exist, but we're not likely to be able to see them, let alone find experimental tests, observational methods to find something that we don't know what we're looking for. So at this moment in our history, following the water is our best bet to finding life. Well, let's just think about the water molecule for just a moment. H2O, probably, the only chemical compound that many people in the general community are aware of. You folks probably very different, you know all sorts of chemicals, but H2O, 2 hydrogen atoms and 1 oxygen atom. Hydrogen is the most common element in the universe, literally 99% by number and about 75% by weight. And it was formed shortly after the Big Bang. That is to say, as the universe cooled sufficiently to move from radiation domination to matter, material domination, then that's when both hydrogen and helium formed. 99.99, a few more nines, percent of all material that came into existence as a direct result of the Big Bang, hydrogen and helium. But as hydrogen began to clump together, as the nuclear fusion processes began to fire up inside stellar cores, other elements began to be formed. And depending upon the mass of those stars, and we're not going to go into stellar evolution in this presentation, but depending upon the mass of the star, a differing range of elements could be produced. But outside of hydrogen and helium, the next most common element in the universe is oxygen. Generally speaking, created in stars a touch heavier than our own sun. It's a natural process, a natural nucleosynthesis process that happens in slightly more massive stars than our sun. So it should not be too much of a surprise when you think that hydrogen, the most common element in the universe, and oxygen, the third most common element in the universe, have come together in such large amounts all throughout the universe. As I said, if you go back 50 years ago, the notion that water would be common was not a common notion. It wasn't a commonly held view. But today, given what we now know about the universe, and when we think back to the nucleosynthesis process, it really shouldn't be such a surprise that H2O has gotten together in as large a quantity as it has around not just our solar system, but indeed around the universe as a whole. Just as a little bit of a tip of the hat to my chemistry colleagues, the periodic table. 92 naturally occurring elements and their various isotopes. But this time, the perspective is from the point of view of how were these elements created? And you can see hydrogen and helium obviously associated with the Big Bang, but the other processes that happen on an astronomical scale associated with the nucleosynthesis of elements inside the cores of stars, and then through nuclear and other nuclear processes that happen after supernova eruptions, the merger of neutron stars and black holes, and so on. It puts a whole new spin on chemistry. I actually rather like the periodic table after I look at this rather than before. Okay, so hopefully I've convinced you that H2O, in fact, should be floating around in one form or another, solid, liquid, or gas, in significant amounts around the place. We're going to stay fairly local in this presentation. We're going to hang out in the solar system more than anything else. More often, more reason than not, simply because we were sort of bound by time. Let's have a look at our solar system. Outside of the sun, the other objects in our solar system, primarily the planets, there are 8 of them, and we can talk about Pluto's demise over a coffee or something stronger. Asteroids in the asteroid belt, out in the Kuiper belt, and of course comets. So there's a lot of material floating around our solar system in orbit, gravitationally choreographed by our sun. All of these objects surprisingly have interesting histories with respect to water, past and present. We'll start at home, okay? No place like home, so to speak, and it's apparent to everybody that water is a significant component of our planetary environment, our hydrosphere. Now, as a fraction of the total amount of mass of our planet, the amount of water is actually relatively small. We're planet, 12,500 kilometers in diameter, give or take. And on average, the surface depth of water is definitely less than 5 kilometers. So, do the arithmetic, figure out how much water is there as a fraction of the total mass of our planet. Okay, water is not that large a fraction. But where it is located has allowed life in a huge array of forms to exist over the last, roughly speaking, 4 billion years. Life came into existence on our planet somewhere in the vicinity of 3.8, 3.9 billion years ago, when our planetary surface cooled sufficiently and our atmosphere had, sort of populated sufficiently that liquid water could begin to exist on our planetary surface. And herein lies the first question that I'm going to throw at you. Here I am saying that, water is a relatively important component, yet a relatively small component of our planet. Where did it come from? 12,500 kilometer diameter, molten mass of material formed 4.5 billion years ago as our sun's nuclear furnace fired up. Most of our planetary interior is very solid material, much denser than water. In fact, by the time you get to the core, we're talking about sort of, solid iron, so as to speak. But on the hydrosphere, we've got a lot of water. Where did it come from? Two primary sources. One associated with the outgassing of our interior. In other words, as our planet cooled and it solidified, it was sort of squeezing out the volatile materials, the volatile gases that were trapped within the material, and forced that low density material upwards and outwards onto the planetary surface. And because we have a reasonably strong gravitational field for our planet, because by this point in time there was enough outgassing onto our planetary surface that nitrogen, carbon dioxide in particular, and water vapor to a lesser extent, they were able to exist in our atmosphere, and the water vapor was able to cool the water cycle, if you will, of condensation and evaporation. So there is no doubt that a fairly significant amount, whether or not it was the majority is up for huge debate, but a significant amount of water vapor came out from our interior and then coalesced, condensed onto the planetary surface, forming our primordial oceans. So this is in the vicinity of 3.8 billion years ago. But we are also now of the view that a significant amount of the water in our oceans, and again, we don't know whether or not it's the majority, arrived here courtesy of cometary and asteroidal impacts. That is to say, the debris, if you will, left over from the solar system's formation that did not form into the larger planetary bodies, or indeed even the asteroidal bodies in and around the asteroid belt between Mars and Jupiter, or out in the Kuiper belt. But smaller material that were in much more eccentric orbits, not nearly so well bound in these sort of regions like the asteroid belt, the cometary materials and sort of the Apollo asteroids flowing into the inner solar system, probably being helped along by Jupiter's gravitational field, throwing rocks at the inner solar system. And these materials, comets and asteroids, contain a significant amount of volatile material, in particular ices. And when they slammed into the Earth, of course, they gave us their H2O, initially in the form of an ice. The impact vaporized it, put it into its atmosphere, but then the cycle of condensation took place, and we have our oceans. So it's highly likely that the majority of the water that we see on our planet was a combination of these two processes. So given the fact that we're in a bit of a conundrum, did the majority of our water arise from the planetary outgassing process, or did it arrive here from outside of our planetary environment, the comets and the asteroids? Well, how do we figure that out? How do we look backwards in time and decide which was the principal component that led to water on our planetary surface and thus led to life? We are able to track what we call the deuterium to hydrogen ratio that exists in water and exists in ices. And the argument goes that when we look at our own ocean, the deuterium to hydrogen ratio, the D to H ratio, has a specific value. And that is very environmentally specific. Deuterium, you might recall, is an isotope, excuse me, of hydrogen. It has an extra neutron in its nucleus, making it a little heavier. And the incorporation of deuterium instead of hydrogen into H2O, so D2O or HDO and so on, how much of that is present in a body of water is very much dependent upon things like evaporation rates, because D2O is not going to evaporate as easily as H2O. So the D2O, the D2H ratio gives you a bit of insight into the planetary environment, and is a bit of a signature that says, hi, I came from fill in the gap. So we know what the D2H ratio is here on Earth. When we look out at comets, for example, you know, the cometary tails spewing behind them, really easy to actually pick up that D to H ratio. And we've been to other planets, and we've been to a couple of asteroids. So we know a lot of D to H ratios around the place. If cometary material was the primordial ingredient that gave more water to Earth than our outgassing process, then our D to H ratio should match up with cometary D to H ratios. Well, nothing in astronomy is easy. Some of the cometary ratios do match our D to H ratio here. Many do not. Some from the inner solar system, you know, the asteroid belt area, asteroids in particular, they've got pretty good matches for the D to H. Short period comets that sort of loop around the inner solar system, some of them do match, not all. Out in the Kuiper belt, longer period comets, let alone the comets that are coming in from the Oort cloud, again, there is quite a variety of these D to H ratios. So it's not at all clear at the moment whether or not the investigation of these sort of rogue elements, shall we say, these comets, is giving us a clear picture on whether or not it was cometary impacts that gave rise to more water on Earth than our outgassing process. But it is a very active, ongoing search for understanding, and it also highlights how much water is actually still running around the solar system in the form of comets and asteroids. Well, speaking of comets, just to remind you what a comet is, it's an object that has a nucleus that's a few kilometers in diameter, maybe as little as 1 kilometer, maybe as high as 15 kilometers, but in a few kilometer diameter range. And it is, to use Fred Whipple's term, a dirty snowball. It's a composite of material, fairly loosely held together, not particularly solid, but that loosely held gravity material is primarily sort of the silicate rocks and icy mixtures, the sort of stuff that you would find in your own backyard here in Toronto at this time of the year. If you could dig into the soil, you would pull out garden variety soil mixed liberally with water, ice, snow. That's the sort of stuff that a cometary nucleus is made of. And as the comet's nucleus swings in towards the sun, remember these are in elliptical orbits, when they're far from the sun, the deep chill of space keeps them together and, you know, keeps them fairly quiet. But as they swing in towards the sun, they begin to outgas in a fairly feverish fashion and sport these tails that you see on the screen in front of you. The volatile materials, not just water vapor, methane, hydroxyl radicals, carbon dioxide, carbon monoxide, there's a whole range of volatile materials that are trapped within the substrate of the cometary nucleus. That material, as it heats, gives us the opportunity, spectroscopically, to analyze the composition of the cometary nucleus, because the tail, of course, spreads out over potentially millions of kilometers. So it's a fairly easy thing to trace the D to H ratio, the volatile history of any given comet. And we find sort of several dozen new comets every single year. You've all heard of Comet Halley, probably, but there's many comets. As I said, 2 to 3 dozen new ones every year that we find. And we are of the view that out there in the Oort cloud, this huge spherical volume that surrounds our solar system, there are truly billions of cometary nuclei. And they get mixed up periodically, churned up, and rain new comets down into our inner solar system. We have visited, as I said, a couple of comets. This is perhaps the most recent cometary encounter. Churyumov-Gerasimenko was the Rosetta spacecraft. It actually landed on this well, they called it the rubber ducky. You can see why. You know, it's a loosely held composite of material. It's about 4 kilometers long, give or take. Bulbous. Interestingly enough, a lot of objects in our solar system are this sort of merger. We suspect that, you know, this was two distinctly roundish rubble piles that coalesced and created the shape that you see here. But this long exposure image, you can see the streaming rays of material coming off the comet. And that was why Rosetta from the European Space Agency went there to examine this comet in unprecedented detail. And it did a wonderful job for a couple of years. And it followed the comet into perihelion as it came through closest approach to the sun. So we got a really good breakdown of how this comet was behaving during its most active period. And so again, of course, amongst other things, D to H ratios and so on, we measured the bulk density of this object, compared it to its volume. The density is barely that of water, so it is very, very loosely held together. But it's those types of space missions that give us improved insight into, you know, the cometary makeup, the cometary mixtures of material. As I said to you, comets are prolific in our solar system. This gives you a bit of a feel for how many comets we really do suspect, or at least cometary nuclei exist out there. And it also shows you the scale. It shows you the Kuiper belt, which is out just beyond the orbit of Neptune for, you know, a couple of hundred AU, astronomical units, and how there are probably tens of thousands, hundreds of thousands, maybe even millions of cometary nuclei there. They're hard to see. But surrounding the solar system is a much larger repository of cometary nuclei, and that's the Oort cloud. So as I said, there is no shortage of raw material out there that is rich in volatiles, including water. And as these nuclei stream into the solar system over literally millennia, so too do we deposit more and more water vapor into the inner solar system. And of course, when they're slamming into objects, which they do given enough time, they of course deposit large sheets of ice on those worlds. Well, speaking of those worlds, around the Earth, of course, we have this wonderful object called the moon. And for the longest time, we thought the moon was one of the driest, most arid places in the solar system. Well, it's not. There is a surprising amount of ice on the lunar surface, probably not interior to the surface. The moon in that regard is relatively dry. It's a low density object by comparison with the Earth, for example. But recent studies using both radar as well as surface probes have revealed that particularly in the deep, dark craters around both poles of the moon, where the craters are perennially shadowed on the floor, no sunlight directly able to reach some of those crater floors, ice has survived in significant quantities. So you can see here over in the South Polar region, the blue here really is representative. This is a false color, of course, but it gives you a sense of how much water is residing in the deep shadowed craters. And so for a place that was meant to be arid, we've rethought what is happening here. Most of this water we think has been transported by cometary impacts. Remember, the moon has no atmosphere. And so the only way water survives through cometary or asteroidal impacts is if that material lands in a shadowed area, and with no atmosphere, there's no conduction from air molecules. The ice remains ice in the absence of radiant energy from the sun. And so over 3.5–4 billion years, particularly during the late heavy bombardment 3.5 billion years ago, the moon was peppered with asteroidal impacts, cometary impacts. So it's perhaps not too much of a surprise that we have as much ice buried, well, just buried, subsurface on the moon itself. When we look inwards to the inner solar system, the planet Mercury, one of the hottest places in the solar system, you would never have thought that ice would have survived on the surface of Mercury. But guess what? Radar imaging, as well as satellite photography, has revealed, and spectroscopy, has revealed that there are significant quantities of ice, you guessed it, in the deep shadowed crater regions around the poles of Mercury. We've seen this, as I said, from radar images from Earth, but we've had a couple of spacecraft over the decades that have investigated in great detail the surface of Mercury. And this is down, I think it's near the South Pole, Kodinsky crater, and it's permanently shadowed, Permanently shattered regions, if they've been impacted by comets and asteroidal material, have deposited ice, and the ice survives, despite the fact that the average surface temperature on Mercury is 400 degrees. Just popping back to the moon, by the way, for a moment, having that much ice is really, really helpful to the idea of, a lunar settlement. The ability to not have to take all the water with you to the moon, to be able to harvest ice from the lunar surface, obviously for drinking purposes, break the H2O down into hydrogen and oxygen, fuel cells, as well as oxygen to breathe. The ability for us to be able to utilize these vast reservoirs of ice is really, really tempting. I don't think we're going to do that on Mercury anytime soon, but the point I make is that even in hot, what you would think of as hostile environments, H2O is in significant amounts inside these deep craters. Even on Venus, there is indication that Venus had a relatively watery past. Now, today, the average surface temperature on Venus is even hotter than Mercury, and you can barely survive atmospheric entry for a comet or an asteroid because of the very, very thick atmosphere. It's 90 times thicker than the Earth's atmosphere. So having any form of ice deposits on the Venusian surface today is probably a non-starter. There is just too thick an atmosphere that's too hot. However, there are indications that water erosion probably did happen on the Venusian surface. And we're talking back now 2, maybe 3 billion years ago, before the runaway greenhouse effect took hold, thickened the atmosphere, and raised the surface temperatures. Back in the earliest days of the solar system, 4.5 billion years ago, while Venus is definitely warmer than Earth, it probably wasn't inhospitable to the point of, no, we can't even have water on the surface. The surface temperatures on Venus probably were sub-boiling point. I know that doesn't sound particularly attractive, but nonetheless, if it's below the boiling point, then liquid water can exist on a planetary surface. And it's likely that on Venus, that was the case. The outgassing on Venus was probably comparable to the outgassing on Earth. The bombardment we experienced, Venus probably experienced. So while the atmosphere was still modest in terms of its thickness, it is likely that water flowed on the surface of Venus. But over time, with an increasing amount of carbon dioxide in the atmosphere, the runaway greenhouse effect, as the temperature soared, well, now you have a problem for liquid water on the surface, and it became vapor. There is water vapor in the planetary atmosphere. And when you get up to altitudes of 40, 50, 60 kilometers, the temperatures actually become modest. And of course, there still exists water vapor. So we now enter the realm of science fiction. Can life exist at altitude on Venus, given the fact that water vapor is available for those forms of life? Who knows? There's certainly no indication at the moment that life exists on Venus, but it's a wonderful place to speculate. Again, though, the takeaway story here is that Earth, Moon, Mercury, Venus, all have got watery histories. Okay, the planet that we just love to talk about, Mars. Okay, Mars is today a very arid environment, very thin atmosphere, and ice deposits all over the surface. If there's ice deposits all over the surface, that begs the question, was that ice once in a watery format? The image on the right is speculative, but based upon our understanding of Mars's evolution over the last 4 billion years. Based upon the surface geometry, geology, the surface chemistry that we have picked up from all of the spacecraft that have gone to the surface, have orbited, we know that Mars had a very watery past. In fact, Mars may have been more hospitable than Earth back 4 billion years ago, because this is a planet that would have cooled faster, would have outgassed further. And because it's further from the sun, any of that outgassing atmosphere would have been retained back for a reasonable period of time, as in 500 million years, maybe 1 billion years. But that same atmosphere was about to be subjected to no protective magnetic field. And so the environment of Mars had to change as the sandblasting activity of the solar wind stripped away the Martian atmosphere. But not before a significant amount of groundwater erosion etched into the planet's history, waiting for us to read it. We still see volcanoes present on the planetary surface. We see atmospheric cloud. Oh, it's thin stuff, and it doesn't rain because the atmospheric pressure on Mars is only like 1%. But nonetheless, there is water vapor in the atmosphere, and there is this water recycling process which takes place on Mars. But as I said, the planetary surface is rich in the signals, the signatures associated with water erosion. The image is on the left. Now, the lower image, yeah, maybe some of that was associated with rocky material erosion, creating some of these gullies. But the upper image is definitely associated with water that has tracked through the Martian surface. The image on the right is a time sequence associated with about 12 hours, showing how the surface seems to darken during the day. And given the fact that spectroscopically we know that there's a rich amount of salt associated with this darkening process, the speculation is that the subsurface ice mixed with a significant amount of salt at the warmest temperatures that you can get on the planetary surface, approaching -0 degrees, has allowed for brief periods per day a watery brine to form, which then dissipates back into the soil as the temperatures begin to decline. Here again in Canada, we know the effect of salt on water to lower the freezing point. And so there are lots of surface indications from satellites that Mars still has an active water cycle. But we know full well from those orbital measurements that there are large, huge sheets of ice beneath the subsurface of Mars. This is an image from the Mars Reconnaissance Orbiter, which has been in orbit since 2005, showing literally hundreds of square kilometers of ice beneath the North Polar regions on Mars. Now, the question is, are those ice sheets real ice? Because really what we're picking up is the presence of hydrogen. But if you're picking up such large quantity imagery of hydrogen, it is highly likely that what you're doing is picking up the H2 in H2O. To confirm that, we sent a spacecraft by the name of Phoenix there in 2007 to land at about 70 degrees north latitude to dig into the soil and ascertain whether or not the imagery and the radar imagery that we were picking up from orbit really was ice. Nothing like getting a shovel in the ground and digging around the place to absolutely confirm what your remote sensing information is telling you. The very first image that Phoenix took of the area beneath the landing pads revealed sheets of ice. The landing retrothrusters had cleared away the relatively dusty surface and revealed ice sheets. And then, of course, the robotic arm dug into it. We verified that it was water. And indeed, even better, it was water that you could drink. The pH value was right up there with human consumption. So Mars definitely has a huge amount of ice on the surface. It is still an active area of research as to whether or not artesian water exists, flowing water beneath the surface. Many people believe it is, but there is certainly ample evidence on the surface of past flowing water and still bodies of water, and we see the residue of that in the form of ice on the surface today. So this is a planet that was rich in water. And if it was rich in water, the question naturally arises, was it rich in life? Did life gain a foothold on Mars, potentially even before it gained a foothold on Earth? And if the resilience of life that we see here on Earth, think of extremophiles, if the resilience of life on Mars was every bit as much as it is on Earth, maybe life has survived subsurface today, either in the artesian regions beneath the surface, or maybe just subsurface near bodies of ice. We don't know. But there is certainly big efforts underway to clarify that picture. And in fact, next month, there will be 3 spacecraft that will arrive at Mars, one of which the Perseverance rover, that is designed to look very, very explicitly for the signatures of life. I do have to throw this in, by the way. What better country to figure out that it snows on Mars than Canada, right? Part of the Phoenix mission, the LiDAR instrumentation, the surface observation equipment, the weather station basically, was built here in Toronto at a company called Optech. And the imagery that the LiDAR system picked up was second to none. We did great things with Phoenix, both on the ground and in the atmosphere. Well, this shows you a cloud deck. Remember I told you there were clouds? At about the 4-kilometer altitude level. It is water, H2O clouds, and you can see these streamers falling away from the cloud. LiDAR picked it up. Those are streamers of water vapor that had condensed into ice, into snow, and was heading towards the ground. No, you're not going to ski on Mars anytime soon, okay? This stuff doesn't really reach the ground in significant amounts, coats it at best as a light dusting. But nonetheless, the process whereby water vapor forms ice crystals and then clouds, which eventually fall to the ground in the form of snow, was detected by the LiDAR instrumentation back in 2008, excuse me, launched in 2007. As I said, we've sent to the surface lots and lots of missions. The Curiosity rover went down into Gale Crater. It was a site associated with a lake in the past, watery environment. Curiosity, within literally the first few weeks of arrival, was able to determine with its geological investigations the existence of past flowing water, basically sedimentary material, various minerals that could only form in the presence of both liquid water flowing as well as stagnant. So the investigation of Gale Crater has been ongoing now for 8 years. Curiosity is doing its best imitation of a mountain goat and is climbing Mount Sharp, which is a 5-kilometer tall peak right in the middle of Gale Crater. And you can see Gale Crater, you can see the foreground area of Gale Crater, and in the middle, that is Mount Sharp. And Curiosity continues to make its way up Mount Sharp as we speak. Okay, I think I spoke about this a little bit out of order. I just gave you the rundown of how the Martian environment has changed. So I'm just going to move past this slide. Once we move past Mars, we're into the asteroid belt. Millions of objects, small in size, generally speaking, but as large as, say, Ceres and Vesta. Ceres is a dwarf planet. Vesta is about 500 kilometers in diameter. These are significant sized objects, which for the longest time we thought were relatively boring and relatively uninteresting until we sent spacecraft there. And then we realized that we really didn't understand these objects nearly as well as we thought. You can see there Ceres on the right-hand side, and you can see those two little white dots in the middle of the image, Ocata Crater. Those are salt deposits. Salt and salty brine deposits exist on the surface of both Vesta and Ceres. These two objects were both visited by the Dawn spacecraft over a number of years. First ion propulsion vehicle that was able to fly around from one object to another outside of the Earth-Moon system. Vesta and Ceres by Dawn, the only time we've ever broken free of one gravitational orbit and moved into the gravitational influence of another object. Takeaway message from Dawn's investigation of these two objects, again false color, is that both of these objects, particularly Ceres, are rich in subsurface water deposits. Probably in the form of ice, although there's a little bit of debate with respect to Ceres. Maybe there is some subsurface liquid, but definitely icy deposits on the surface, lots of salt. And when you mix salt with ice and can get some temperatures up towards 0 Celsius, then maybe you are also seeing some liquid. We actually see fog in some of the deeper craters on Ceres. So again, the inner solar system, Mercury, Venus, Earth, Moon, Mars, out into the asteroid belt, lots and lots of ice. And of course, we probably all have heard about the Jovian moon Europa. First discovered to have a serious amount of ice on its surface by the Voyager probes back in, well, actually the Pioneer probes and then the Voyager probes in the 1970s. This is one big ice ball. But more interesting is that beneath the ice ball is a subsurface ocean. And we've even detected with the Hubble Space Telescope geysers of liquid water being forced out of that icy surface. This is a world, it's about the size of our own moon, about 3,500 kilometers in diameter, that not only has a subsurface ocean, but it's likely to be quite warm, courtesy of the tidal influence of Jupiter and the other Galilean satellites. Warm water. Now, it doesn't see any photosynthesis. It doesn't see any sunlight because obviously it's a completely covered ice ball, but there's no shortage of life on this planet that operates in the absence of photosynthesis. Go hang out near a black smoker volcano in the depths of our ocean. Very inhospitable environment. Life thrives there in the absence of sunlight. You don't have to have sunlight to provide an energy source that life is able to latch onto. So there's lots and lots of speculation and lots of excitement about what might be beneath the ice coatings of Europa. And there are many missions that are being contemplated to go and search for life on Europa. One of the more ingenious missions being proposed, not planned yet, proposed, is to send a submarine there. Okay, how, of course, you're going to burrow through 5, 10, 15 kilometers of ice to get a submarine into the water. Oh, yeah, the stuff of science fiction. But nonetheless, Europa is a fascinating world. The largest satellite in our solar system, Ganymede, one of the companions to Europa, also has a subsurface ocean. Not probably quite as extensive as Europa, and it is definitely subsurface in contrast to that icy sphere that surrounds Europa. Ganymede is a much more traditional world with a rocky surface, a crustal environment, but it has its own magnetic field, which is how we've been able to trace the existence of liquid water beneath its surface. This is obviously a model, okay, based upon observation of secondary parameters. We can't measure directly the depth of water there, but this is the best model that we have showing the subsurface environment of Ganymede. So two satellites, two of the largest satellites orbiting Jupiter, both significant quantities of water. And if you've got lots of liquid water and it's warm liquid water and you've got lots of salts and other nutrients, again, speculation runs wild about the possibilities of life. Almost done. Out to Saturn. This is the tiny little satellite Enceladus. Really the last place in the solar system we would have ever expected to have found a significant amount of water. And I'm meaning water, not even ice here. We're talking water. Enceladus is, give or take a bit, 400 kilometers in diameter. It's a rocky object that really nobody was terribly interested in until the Cassini probe, which was orbiting Saturn for some dozen years, flew through a plume of water vapor. Completely unexpected. All of a sudden, Enceladus made it to the #1 of the hit parade. We were really interested in looking at this little satellite. It flew, Cassini flew by Enceladus many, many times. It examined the tiger stripes, which are huge cracks in the surface, which were allowing water to be pushed out from the interior. Again, probably tidal action from Saturn. The tidal interaction with this object and other satellites was squeezing the interior, forcing water out into the vacuum of space. You can see the geysering activity. These are real images. This is not science fiction. These are real images. And not only is it water, it's salt water. And so the imagery that we have collected, the analysis, modeling we've done of Enceladus suggests that there's a significant interior volume that is full of water. Again, water, warm water, salty water. The speculation is life. So I hope I have convinced you over the last 45 minutes or thereabouts that water is in fact incredibly common, not only in our solar system. I haven't even spoken to you about the amount of water that we've found in giant molecular clouds and other nebulae that are scattered around the universe. We've detected signatures of water in exoplanetary atmospheres, but just in our solar system. And we are not of the view that our solar system is particularly special, okay, that it is a normal, run-of-the-mill, everyday solar system. Water is everywhere, both in the form of liquid as well as ice. And so if there is that much liquid water around in our solar system, and we are convinced that water leads us to life, it certainly suggests that life is common, not just in our solar system, but elsewhere in our galaxy. Thank you.
Thank you, Professor Delaney. That was amazing, as per the usual. In the chat, we've got a couple of questions. So, concerning the moon, is it confirmed that it has water?
In the form of ice, absolutely. Down in the south polar regions, we have taken radar imagery in the shadowed craters, and there is no doubt there are sheets of ice there. We've also plowed, there was a mission, I guess it was about 12 years ago now, maybe 10 years ago, called L-Cross, where we slammed a rocket booster into the surface of the moon, and then we followed that rocket booster in with a little probe that measured the composition of the plume of material that had been blown up, so to speak, by the L-Cross booster before, unfortunately, that probe also slammed into the surface. And the information that came back, about 5% by weight, was water vapor. So yes, there is no question that there are surface deposits of ice on the moon.
Awesome. Secondly, in retrospect to your speaking on Venus and its vast similarities to Earth, did Venus perhaps have some kind of life at one point?
I guess you can't rule it out because it would have outgassed. The early history of Venus was likely really, really similar to the early history of Earth. And by early history, I'm meaning the first 500 to 1 billion years. So life found its way into existence here at about the 3.8 billion year mark. Assuming Venus's composition and its degree of battering by comets and asteroidal material was comparable to Earth, and again, we have no reason to disbelieve that, then liquid water could well have existed on the surface of Venus in and around the same time as here on Earth. Whether or not that allowed life to gain a foothold, because shortly thereafter, the amount of carbon dioxide in the atmosphere began to climb, and in the absence of water to dissolve the carbon dioxide, that carbon dioxide gaseous component increased quickly. And so the runaway of greenhouse effect probably started, and here again, we're modeling and speculating, but probably started about 1 billion years ago. 1 billion years after formation, and it just got hotter and hotter, and that dissipated the water on the surface. So life at best probably only had 500 million-ish years to stake a foothold on Venus. Well, here on Earth, we didn't get very far advanced life forms in the first 500 million years. It really was pretty simple stuff. So we're now entering an area which I'm not confident to speak on. My astrobiology colleagues are better served in this regard, but it does strike me that 500 million years may not have been enough time for life to adapt well enough with the changing, hotter conditions on Venus. But life, as I've said, is very tenacious, so maybe?
Certainly, yes. We have another question here. Why hasn't the Martian ice been sampled for signs of life yet?
I guess the short answer is until the last decade or so, the search, let me back up. Going to Mars is costly. And when you build instruments to go to Mars, it's a competitive process. So what do you want to find out with the limited resource that you have? If we could send probes sort of willy-nilly and money was no object, you could send a vast array of differing instruments and really get to the bottom of a multitude of questions. We don't have that luxury. So every mission that goes has a series of science objectives to answer. Generally speaking, after the Viking probes back in 1976, most scientists were of the view that life could not exist on the Martian surface. Viking went with a distinct life sciences package to search for signs of life. And while we could talk about those results and some of the speculations that exist to this day, 40 years after the surface landing, generally speaking, for the next 20 or 30 years after the mid-1970s, people didn't think Mars was alive, had any life. And so they focused on geology, they focused on atmospheric processes, they focused on bigger questions associated with the environment and didn't give as much weight to the question of life. With Curiosity, 2012, that began to change. And the ability for Curiosity to sniff methane, for example, a biomarker, to be able to examine the surface for long chain carbon molecules, that began to take on new interest and importance. But that's been the only US lander since, in the last 8 years, that's been the only US lander. Perseverance has a suite of instruments that is much better focused on the search for organic molecules. So it's really been a cost-benefit analysis with missions in the past, the importance of water, the ubiquitous nature of water, and now the importance to astrobiological questions has begun to assert itself. And so you will see more instruments on the ground, starting with Perseverance, looking for those signatures of life. But in the past, as I said, for a while, we just didn't think there was anything that could be there. Now that thinking has changed.
Wonderful, thank you. Another question, what allows water to remain on the surface of Mercury?
The fact that the shadowed craters are completely shadowed. So again, there's no Mercurian atmosphere. And so if you bury subsurface just a little bit, ice in a crater which never sees sunlight, then there's no radiant energy to vaporize it, and with the low gravitational field of Mercury, let it escape into space. So ice can survive in the dark shadows of a crater because there is no conduction from atmospheric molecules to warm up the ice. So as long as the ice fell and formed inside craters from asteroidal impacts, cometary impacts, then sunlight can't get to it and can't evaporate it. So it's only in the polar regions that we have detected ice on Mercury. Out in the plains at other latitudes, no, there is no signs of ice, but that doesn't surprise us. But in these deep, dark craters, yes, ice can survive.
Again, wonderful. Yet another question. The rings of Saturn consist of ice crystals?
In part, but not entirely. If you grab one of those icy snowballs that I mentioned earlier, a mix of silicates and water vapor, smash it into smithereens and smear it around into the ring structure of Saturn, then that's more or less what you've got. So a small portion, I'm not sure what the fraction is, but it's not very large, a small fraction of the ring material is icy, but much more of it is rocky. So it is an ice rock mix, but predominantly it's rocky material.
Awesome. Here's a more conceptualization of a question, more sci-fi. Is it possible that a city on a gas planet, such as the one on Star Wars, The Empire Strikes Back, is possible?
Well, I guess the answer has to be yes, it's always possible, but you're looking at a level of technology that is truly in the realm of science fiction at this moment in time. Gas giants do have water vapor in their atmosphere. So, collecting water vapor, distilling it, creating water. I guess if your atmosphere, if you're above the turbulence of an atmosphere, then sure, you can, create something that has enough lift, if you will. So that means engines and that means fuel. And putting aside some of those basic technology questions, sure, an atmosphere, even in a gas giant, does have enough water vapor that you can trap it and use it. But when you look at the gas giants in our solar system, Jupiter, Saturn, Uranus, and Neptune, they're all fairly inhospitable. They're all pretty rough and rugged atmospheres until you get really, really high. And there's lots of radiation. I mean, there's lots of complications. So I love Star Wars, rest assured. But technologically speaking, we're a long way from getting close to being able to marshal a city in orbit around a gas giant.
Certainly. What do you think is the biggest technological hurdle to overcome in terms of searching for life signatures or space exploration in general?
Probably radiation. We live here on the surface of the Earth in a really protected environment. We have this magnetosphere that deflects away charged particles from the solar wind, and our thick atmosphere protects us in large measure from really damaging cosmic rays. Anytime you get outside of the Earth's protective environment, radiation really is dangerous. Talking about living on the moon, talking about living on Mars, talking about living in deep space, you have to find a mechanism that will allow your human cargo to be protected against such harsh radiation environments. It can be done, but it's not cheap. And there's a lot of effort going into creating materials, light materials, that are really significant blockers of radiation. You know, the International Space Station, for example, when it looks as if there's going to be a serious solar flare or an increase in solar radiation, particulate radiation flowing through the Earth's environment, space weather, and so on, the International Space Station, astronauts sort of hunker down inside the areas which are surrounded by water. Water is a really, really good protector of radiation. So we know how we can do it. That's why you hear about people going to the moon and living in caves, subsurface environments, get the rock surrounding you. Can't do that when you're flying through space. So I think one of the biggest challenges, which we are working on, is really protective radiation environments.
Yes, indeed. I believe this question is asking how are we able, or in future, how are we going to be able to travel long distances?
I could be glib and say slowly, but I'll give you a more definitive answer. Our technology is really poor at the moment as far as long distance travel is concerned. I mean, again, this crowd, you all watch science fiction. It'd be great if we could have a Stargate wormhole. It'd be terrific if we had a USS Enterprise lying around the place. But at the moment, we don't have any of those. You know, the Voyager spacecraft, which are our most far-flung and most rapidly traveling spacecraft, are going to take tens of thousands of years to get to the vicinity of another star. So our technology is really, really up against it at the moment. We could do solar sailing around the solar system. We can use ion propulsion, but all of that is a relatively slow process. Chemical rockets are definitely not the way to go, because that means you've got to carry a lot of fuel with you. So we've got to find ways to utilize sort of, you know, interplanetary or interstellar ramjets, where we can utilize the natural environment of hydrogen and, you know, find, say, a nuclear fuel cell, which will allow us to, you know, create more powerful ion engines. A lot of people, far smarter than me in the engineering fraternity, are working hard to try and find those propulsive methods which will allow us to go from A to B in timeframes that are measured in decades to centuries, not centuries to thousands of years. There's the century spaceship idea, which talks about a huge arc, you know, 1,000 people moving through space, going through generational changes, moving at, you know, building up at an acceleration near G, near 1 gravitation, 9.8 meters per second squared, which will eventually get you up towards the speed of light. And you use that for half your journey, and then you turn your vehicle around and you slow down for the last half of your journey, and so on. But at the moment, the technology really is very, very poor. And so I think the best we can hope for is moving around our solar system at slightly better rates. Instead of 9 months to Mars, try and get that down to a few weeks. That technology, I think, is imminent, but to be able to get out of our solar system with some of the more exotic propulsive methods that, again, science fiction has suggested, they're not science fact yet, but we are sure working on it. I don't like the idea of being propelled by a billion watt laser, for example. That doesn't strike me as a real good plan. But, you know, for a small little spacecraft like Starship, sure, maybe that'll work. But, you know, I don't know is the short answer, really.
Yes. So there is one last one, and it's a question very dear to my heart as well. It reads, I want to get into astronomy. What are the job opportunities for the astronomy degree?
Follow your dream, of course, is what I will say to you first off. If you want to do astronomy, follow it, do it. You know, it's my parents were terribly worried when I told them I wanted to be an astronomer, because they had no idea what an astronomer did and where they could get a job and so on and so forth. Here I am. Okay, so yeah, it can happen. Just stay the course. The good news is that there is a good call for astronomers around the world, based upon the number of astronomy graduates, master's, PhD students who are coming out. I could tell you lots and lots of stories of the students from York University, because that's obviously where I work, who have ended up in the astronomy field, you know, looking after the Hubble Space Telescope, flight controllers, people who look after major observatories around the world, science programmers who get access to telescopes. there are ample opportunities out there if you want to stay the course. But what I will tell you is that in the process of becoming an astronomer, you really have a terrific degree in physics. You've got a great degree in mathematics. You've learned how to computer program, sometimes even better than computer programmers. I hope I haven't got any computer programmers out there. But nonetheless, you've got to learn a lot about computer programming to work with physics and work with astronomy. So at the end of your undergraduate degree in science, you might be specializing in astronomy, but you are very well placed to do all sorts of things. If you decide that, going on for the next X years of study, master's and PhD, is not really what you want to do, but rather you want to get out and raise a family perhaps, and just get out into the real world, financial institutions love your ability to problem solve. They really do believe that physicists can problem solve and utilize, math and statistics skills second to none, only second to mathematicians. So the opportunity for you to go out and use your skills that you have developed for astronomy, but now are using elsewhere, it's really, really a strong possibility. So be open to the opportunities that will come your way. Stay the course for astronomy if that's what you really want, but realize that you'll have a lot of wonderful tools that allow you to be employable almost anywhere.
100%. So it looks like the stream of questions have stopped. So
good. I'm getting hungry.
We all genuinely appreciate you taking some time out of your busy schedule to do this for us. So yes, applause, Spencer. Thank you. So we don't have a Star Talk next month, but what is coming up, however, is a symposium. And the symposium is going to feature guest speakers and myself. We're going to be doing discussions on dark matter, essentially called the mysteries of the universe. So here is, I'm putting a link in the chat to our website, the ASX website. So here you can buy tickets. So if you are not an undergrad, you will pay $5. If you are, however, a student, it is free. Free to attend. We've got a workshop on astrophotography, which I will be doing. We've got some really awesome speakers coming in, and it's certainly not something that you will want to miss. So we also have a Facebook page that you can also consider as well. Thank you, Spencer, for putting that up there. So be sure to keep tabs on what we're doing in the next couple of months. And we hope to see you in our next event. Thank you so much, everybody.
Thank you.